Hello everybody, welcome to today's lecture. Today we are going to do the last part of function of several variables syllabus, that's extreme value for function of two variables. So let us start with defining the same. F of s, which is subset of R2, and f is a function from s to R, be a function of two independent variables x and y. Let AB be an interior point of S. F is said to have an extreme or local extreme value of AB, or eventually f of AB for is said to be an extreme value of f if there exists a suitable neighborhood in AB, neighborhood of AB, such that for all x belong to AB, f of xy minus f of AB does not change sign. F is said to have local maximum or local minimum value at AB according as f of x y minus f of AB is less than, equal to, or greater than equal to 0 for all xy belonging to the neighborhood of A. So let us understand this definition. So what we have is S is a subset of R2 and f is a function from R2 to R. So here somewhere here we have this is S, which is subset of R2. So here points are like AB and XY, and there are points. So this is S, and here we have R. So here we have some point, let us say f of AB, and somewhere here f of XY, which is obviously one dimension. So now what f does is f takes this f of AB to AB to f of AB. So what does the definition says that if we have a neighborhood of AB in which there are x, y's, then in this neighborhood of f of AB, if those f of xy exist and they do not change sign, that is f of xy minus f of AB is either greater than equal to 0 or less than equal to 0, then we say that f of AB is a local maximum or local minimum. I hope you understand this. So now we understand the theorem. So what does this theorem state is? It is the necessary condition for the existence of extreme values. So let S, which is a subset of R2, and f, which is again a function of S to R, and AB be an interior point of S. So everything is the similar as we had in the definition. If partial derivatives f of x, f of y both exists at AB, and f has extreme value at AB, then what we have is f of x at AB is equal to 0 and f of y at AB is equals to 0. So what does it say is, if both the function exist at AB, that is partial derivatives exist at AB, and if f of x at AB and f of y at AB, if the f has extreme values, then these partial derivatives will be equal to 0. So this is the necessary condition, not sufficient. So we need to keep this at mind. If there is an extreme value, then this will be 0. It does not say that if this is 0, then it has extreme value. So we understand this thing by an example. So what is our first example? So example 1, so that the function f of xy, which is f of xy is equals to modulus of x plus modulus of y, and xy belongs to R2, possesses an extreme value, minimum value, or maximum we can say, at 0 0, although f of x y and f of y x, f of x at 0 0 and f of y at 0 0 does not exist. So we need to say so that this condition holds but this does not hold. So let us understand. So let us find f of x at the point 0 0. So we know the formula. So it is limit h tends to 0, f of 0 plus h comma 0 minus f of 0 0 divided by h. So which we have is, here we will have modulus of limit h tends to 0, modulus of h divided by h, which is equals to plus 1 or minus 1 according as h is positive or negative. So hence this limit does not exist. Similarly we can say that this also will have positive 1 or negative 1 according as k is positive or negative, and hence we can say that the partial derivative does not exist. So we now see for the other case. Now f of x y is equals to modulus of x modulus of y, but this is always greater than f of 0 0, because f of 0 0 is obviously 0. That means f of x y minus f of 0 0 is always greater than 0, and hence what we have is the property of extremum. So we can say that the condition the theorem that we had stated is necessary, but it is not sufficient. So we now define. We go to a definition. Let S subset of R2 and F from S to R. So again we have the same condition. S is a subset of R2 and F is a function from S to R. An interior point A from AB of S is said to be a stationary point of F in S if both f of AB and f of x partial derivative with respect to x at AB and partial derivative of y with respect to y at AB exist, and f of x, so it's said to be a stationary point if its both partial derivative exist at this point AB and it is 0 and its value is 0. So let us try to understand this. I hope this suffices. So what does stationary point mean? A stationary point is an interior point in which the partial derivative with respect to x and partial derivative with respect to y both exist and the value is 0. So we now go to the example which says find all the stationary points of f of xy, and f of xy in our case is 4x square minus xy plus 4y square plus x cube y plus xy cube plus 4. So now what we need to understand first is that the partial derivative must exist. So for the partial derivative to exist, the function must be differentiable, as we know, and since this is a polynomial, so it is obviously differential in any plane. So it is differentiable, hence the partial derivative exists. We now need to show that f of x is equals to 0 and f of y is equals to 0, and we need to find the points where this is going to happen, and hence we'll get the points. We need to find the stationary points, right? So we first find f of x at the point x, any point xy, and we get 8x minus y plus, this is 0, and here we'll get 3x square y plus, here we'll get y cube, and this is nothing. Again we'll find f of y at any point xy, and we'll get, so we'll get, this is 0, here we'll get minus x plus, so this is with respect to y, so this is 8y again plus x cube plus 3xy square. Okay, so we get the points f of x is equals to 0 and f of y is equals to 0, implies f of x plus f of y will be 0. This implies if we add these two, what we get is 8x plus 8y, so we can take it together, again minus x plus y, we can keep it together, again this is 3x square y plus 3xy square plus x cube plus y cube, and this is equal to 0. So what we see is this is 7x plus y plus, and this is the formula of x plus y whole cube, so we'll get x plus y whole cube which is equals to 0. So if we take x plus y common in this two, we get 7 plus x plus y whole square which is equals to 0. So from this what we get is either x plus y is equals to 0 or x plus y whole square is greater than equal to 0. Since this cannot be 0, because this is a positive quantity and this is a positive quantity, this cannot be 0, hence x plus y must be equal to 0. Sorry for that. So now what we do is we need to, so we have f of x is equals to 0 and we have x plus y is equal to 0. That means x is equals to some minus y, or minus y is equals to x, we can take anything. So if we put this in this value, what we get is f of x which is equals to 8x plus x minus 3x to the power 4, oh sorry, this is x cube plus, so this will also be minus x cube. So what x cube, so what we get, this equals to 0, implies we get 9x minus 4x cube is equals to 0, and from this if we take x common, we get 9x common, 9 minus 4x square is equals to 0. This implies x is equals to 0 or x is equals to, from this we get 3 by 2 plus minus 1. So it's simple. So what we get is either x is equal to 0 or plus minus 3 by 2. Similarly, if we solve for f of y is equals to 0, because it's almost the similar thing, so we'll get y is equals to 0 and plus minus 3 by 2. In this case we'll get minus plus. So now what we have is the stationary points can be 0 comma 0. Again, when 3 by 2 is merged with the other one, it will be negative, and it is lastly is 3 by 2 by 3 by 2. So these are the three stationary points of the given function. I hope this is clear. We now do with another definition. So definition. So what does the definition say? An interior point AB of the domain of a function f of two independent variables x and y is said to be a saddle point of f if it is a stationary point of f, that is if f of x at AB is equals to 0 and f of y at AB is equals to 0. This will give this stationary point, but has neither the maximum nor the minimum value at that point. So normally we had in the definition necessary condition that the for the extreme value, maximum value, we need to have f of x and f of y to exist at that point, and it must be equal to 0. And in a stationary point we found that it is known as a stationary point if the function the partial derivative have value 0 at that point. So there might have a case, because we have already seen that even if the partial derivative does not exist, we can find out that the maximum and minimum occurs, and it might become that we might have a case that the partial derivative exists and it is 0, but we can't decide whether it is maximum or minimum. Hence we say that those type of point as saddle point. So let us try to find some saddle points by an example. So our example 3 says, so that 0 0 is a saddle point of f of x y which is equals to x to the power 6 plus x minus y whole cube. So here f of x will be 6x to the power 5 plus 3x minus y whole square, and point 1 the partial derivative with respect to x, and again f of y will be this is 0 and it will be minus 3x minus y whole square, because here we have minus y. So we see that both exist at f of x and f of y, and f of x at the point 0 0 is 0, f of y at the point 0 0 is also 0. So we see that it's a stationary point. So we now try to find out whether it is a maximum, minimum or a saddle point. So now in the neighborhood of 0 0 there are points where x is greater than y, and there are points where x is less than y. Thus x minus y is positive for some points and negative for some other points in the neighborhood of 0 0, since x to the power 6 plus x minus y whole cube is greater than 0 when x is greater than y, and it is less than 0 when y is greater than 0 and x is equals to 0, which shows that f of x y minus f of 0 0 does not change sign in any neighborhood of x. This proves does change sign in any neighborhood of 0 0. This proves that f has no extreme value at the point 0 0 and hence is a saddle point of f. So let us consider this point. So if we have we obviously know that the point in this R2, if 0 0 is the point, so we can find any point in this region, in this neighborhood, and we can obviously find a point which is greater than y. We can even find a point x is equals to 0 and y is greater than 0. So let us consider the first point. So if x is greater than y, this is a positive quantity and this is a positive quantity, and hence it will be greater. But if y is greater than 0 and x is equals to 0, then we'll have a negative quantity. And so in this neighborhood, any neighborhood of 0 0, we can find both signs, and hence it does change sign in any neighborhood of 0 0. Hence this is not a maximum or minimum point. Hence there is no extreme point at 0 0. Hence it is known as saddle point. So we now state a theorem. Sufficient condition for existence of extreme value. So this is the sufficient condition. Let S be a subset of R2 and f from S to R be a function of two independent variables x and y. Let AB be an interior point of S such that f of x at AB is equals to 0 and f of y at AB is equals to 0. Let f possess continuous second order partial derivative in a certain neighborhood N of AB. So first thing, everything is the same. So f of x at AB is equals to 0 and f of y at AB is equals to 0. So this was there. So let f possess continuous second order partial derivative in the certain neighborhood AB of AB such that f of xx at AB and f of xy at AB and f of yy at AB are not all 0. So all these two must be 0. We have already seen that, and these are not all 0, so one of them must be non-zero. Then there are conditions. F has no extreme value at AB if we define H by f of xx dot f of yy minus f of xy whole square. So everything is at the point, and if this is less than 0, then there is no extreme value. If this h is greater than 0, then there is an extreme value, and in particular f has maximum value at AB if f of xy, and if f of xy is less than 0, then it has maximum. If f of xx is less than 0, then it has maximum. If f of yy is less than 0, then it has minimum. And if f of x is greater than 0, or if this is greater than 0 or this is greater than 0, then we'll have maximum or minimum. Now if h is equals to 0, we might have a case. So first case, second case, and third case. So if h is equals to 0, then f may or may not have extreme value at AB. So we can conclude for h is equals to 0. So we now try to find an example for this, and with the help of example we find the working of the theorem. So let f of xy, so we have f of xy is equals to x to the power 4 plus y to the power 4 minus 2x square, so that f has a local minimum value at 0, 1, minus 1, 0 and 1, 0, and 0, 0 is the saddle point of f. So for these what we need is f of x. So f of x at any x point x is 4x cube. So let me go directly, x square minus 1, and f of y will be 4y cube. So we have f of x and f of y vanishes at, so if we equate and find everything, so we'll get that there are 3 points, namely this stationary points. So we now find f of xx. So f of xx at 1, 0 will be limit. So let us first find f of xx. So f of xx will be so this is 4x cube minus 4x. So we'll have 3 4s are 12, x square minus 4, and we'll get at the point 1, 0 is 12 minus 4, which is 8. F of xy, if we find similarly, we'll get at the point 1, 0 is 0, and f of yy at 1, 0 is 0. Hence, thus we have f of xx at 1, 0 is greater than 0, and the value h, which was h was f of xx dot f of yy minus f of xy whole square, can also be represented in the metric form as f of xx, f of xy, f of xy, f of yy. And if we put the values, so this is 8, this is 0, 0, this is 0, will give 0. So for if h is 0, then f may or may not have extreme value at AB. So since at this stage no definite conclusion can be drawn regarding the extreme value of f at 1 and minus 1, similarly we can check for minus 1, 0, and we'll have a similar case. In this case, f of xx is less than 0 and the h is equal to 0 and other points are 0. So we have no conclusions. So at this stage, no definite conclusion can be drawn regarding the extreme value of f at 1, 0 and minus 1, 0. Okay, so now f of 1 plus h, 0 plus k minus f of 1, 0. So this is normal neighborhood in neighborhood of 1, 0, and this will be 1 plus h whole to the power 4 plus k square to 1 plus h whole square plus 1, which is 1 plus h whole square minus 1 whole square plus k square. This is always greater than 0. So if we manipulate, we will get this thing, and hence in any neighborhood of 1, 0, since hk are not simultaneously 0, hence f has local minimum value at 1, 0. And again, if we find the other way through, we'll see that is no any neighborhood. Thus f has a local minimum value at minus 1, 0. Now for the point 0, 0, f of x at 0, 0 is equals to minus 4, and f of xy at 0, 0 is equals to 0, and f of yy at 0, 0 is equals to 0. Hence f of 0 plus h, 0 plus k minus f of 0, 0 is equals to h square plus k square, h to the power 4, k to the power 4 minus 2h square, which is equals to h square minus 2 plus k square. For hk is a neighborhood of 0, 0, we have when, so see, when this part can be 0, less than 0. So if modulus of root over h is less than 2, or root over h can be taken here. So if modulus of h is less than root over 2, then we'll have this part is negative, and if k is equals to 0, obviously, so we'll have this part is negative, and for other values it will be positive. So we can't conclude, so hence it is a saddle point. So we now do one more example. So that if f of xy is equals to 2x to the power 4 minus 3x square y plus y square, this is the function, then f of xx dot f of yy minus f of xy whole square is equals to 0 at 0, 0, but f has neither a maximum nor a minimum value at 0, 0. So here we find f of x, and it is 8 h cube minus 6 xy, and f of y also we can find. So f of xx is equals to, so we can find everything. So clearly f of xx at 0, 0 and f of y at 0, 0 is 0, and we'll have f of xx is 0, f of xy is equals to 0, f of yy is equals to is equals to 2. Hence we find that this is 0, the h is equals to 0, and f of xy minus f of 0, 0 is equals to some, so 2x to the power 4 minus 3x square y plus y square, which is equals to 2x square minus y, x square plus minus y whole, and this is greater than 0 if y less than 0, or x square plus y, x square greater than y plus 0 greater than 0, and is less than 0 if for y greater than x square plus, which is greater than y by 2 is equals to 0. Hence f of xy minus f of 0, 0 does not change sign, in any neighborhood of origin. Hence f has neither maximum nor minimum at 0, 0. So similarly we can find other questions. So there are two questions which I give as an homework, and in the next lecture we'll do Lagrange's multiplier for finding extreme values. Thank you for watching this video. Thank you for watching this video. For any queries, join my group in the description, and here you can find the soft copy of the notes of the lecture and update of the next lecture. Do like and comment and share with your friends. Thank you.